Okay, so I'm willing to give you some minutes still, but if I am going to explain a little bit about monads, I think it's best that well, you can decide for yourself. Either you want to follow, and then it's really a good idea to close your laptop, or you say like, I don't want to follow this, and I will just continue working on the Tetris project, which is fine by me. It's just going to be annoying because I'm going to be talking here, so you can choose yourself. Okay, so I already gave it away, but in my lectures I don't like starting off with "we are going to talk about monads" because it frightens people, and also just if at any moment you think, oh, this is really difficult and I don't fully understand, that's totally fine, because the slides that I will be teaching is like lecture 15 of a first year course at university. And there is also like I used material from this web page, which is excellent, and you can read upon this if you would like that. So I'm going to in my head I'm going to try to go painfully slow, because otherwise I will probably go too fast. But if I really go too slow, just tell me, like, Christophe, we get it, just move on. That's fine. Okay, so there are a number of things that I didn't cover yet, that we need to cover first in order for the rest of the slides to make sense. And so the first thing, it's a data type, maybe, which is used very often in Haskell. And so the maybe algebraic data type, it's actually to indicate that something can go wrong, right? So data, maybe, that's the name, right? And then it takes one type argument to be a complete type. And so maybe itself, which kind does maybe have? Star to star, right? And so it has two constructors. The nothing constructor, and that indicates that there is no result. And then just to indicate that there is a result, and the result is this 18, right? And so we have two representations, we have two values to give back. If something went wrong, we give back nothing. And otherwise, if we want to give a result back, we wrap it in a just. So for example, if we want to indicate that the result is 5, how would we, what should we make? We should make a just 5. And the type of just 5, what is that going to be? Do you have an idea?
Just 5, it's maybe over int.
Yeah, good. And so we have two functions here. The first one is divide. And divide, of course, it can go wrong. If you divide by 0, then you just return nothing. You say, okay, this doesn't really have a result. I'm going to return you nothing. And so if we look at the type signature, divide takes 2 int in this case, and it returns a maybe int, right? And so nothing, it has the correct type, yeah? Because nothing, it's a maybe, maybe something, and in this case it can derive that it's a maybe int. In the other case, if it's not 0, well, we can just use the divide of Haskell itself, and we can return just n div m. Everybody's following? Okay. And then for the power, this maybe thing, it can also be used as an argument. Yeah. So if you want to take the power of maybe an integer to another integer, and you give back another integer, well, if it's nothing, then you return 2 to the power n, and otherwise you take out the m from the just, and you take the power to n, right? And so in this case, we have to return something, although here we receive nothing. So it's like a default argument that we implemented here. If we don't provide anything, we just take 2 to the power n, and otherwise we take the provided value m, and we take m to the power n. Okay? So this is something that is used a lot, and so I don't remember exactly where, but in Snake we could have used this. I don't remember exactly where, but somebody yesterday told me, like, isn't it strange that we are here taking, that we are doing something. I think it was when the snake itself is empty and we want to move it or something. Well, in lots of cases, we could have used a maybe there. But as you see, if you divide something, you get a maybe int. It will be percolating throughout your whole program, because the next function that you use, it should be able to deal with this maybe. Yeah? And so for all of the functions that are depend on the divide, they should be able to work with a maybe int. That's really important. So in this case, if you are using maybe, so we divide plus, and we do +3 in this case. So we call divide n by m, and because this m could be 0, we need to anticipate this, and we need to case match. So this is like the assembly version of pattern matching. So you say, here you get a certain result, and then you say, well, if it's nothing, then do this. And if it's just R, take R and add 3 to it. Right? Yeah?
Question on this. Is the compiler always, if we have a data type with 15 possible scenarios, okay? 15 possible constructors, is the compiler always capable of telling us that we skipped one if we have a case expression like this one?
No.
No?
No.
Sometimes it just crashes at runtime.
Haskell doesn't enforce you to have totality. Yes. So you can have partial. If you leave out a nothing, Haskell is probably going to give you a warning, but it just gets really complex because you have very complex types, and sometimes it's difficult or it's undecidable to know all the cases. Certainly with the extensions, but there are systems which enforce totality. So, for example, if you heard about the language Coq, well, in that language you have to be total as well.
But when you don't mess with equality and just pattern match on constructor, it's of course possible to verify the historical cases.
So you can turn on warnings. So, and then if you leave out the nothing case, in this case, Haskell can tell you, in this particular case, indeed, you forgot nothing. Maybe that's an error.
And do you think it's kind of harmful to mix pattern matching on constructor, which can be total, and with pattern matching on just equality, which makes this impossible to check for totality?
I'm not sure that I'm understanding your question.
Okay, if I do it like that, it can be verified by
Yeah.
compiler. But for example, if I change case nothing to this, case just 3 to that, case just something like something else, do other thing. And in this case, this pattern matching involves not only matching on constructor, but matching on some Boolean condition.
Yeah. So then it's not going to be able to verify this for you.
And what what's the best practice about it to avoid such pattern matching? Or
well, there are people that say that you should always write total functions, but it really depends on your use case. But normally, if you don't, if it's not total, it could mean that they run into problems later on, because in case there is no pattern which is being matched, then you will get a runtime error, and so it's good to always write it total, but it's not. Sometimes due to the control flow, you are actually certain that it's not going to run into one of these cases. So it really depends on your application.
but it's not something that people just consider harmful and discourage.
There are people who really think that that want to adjust the pattern matching so that it is total. Yeah. Okay, so on to cloning sheep. It's a while ago, but there was a huge breakthrough in medicine, and so we could suddenly clone sheep. Yeah, and that's fantastic for the medical industry. But it's a bit annoying for programmers, because it's like yet this other use case that we need to take into account when we're writing programs. If we define a sheep, it used to be that every child had both a mother and a father, right? But now with these annoying scientists who have been cloning sheep, they don't necessarily have a father, right? They only have a mother. And so in order to take this into account, we basically have to use this maybe thing. And so we have here a sheep. It has a certain name, and then it might have a mother and it might have a father, and so that's why we put a maybe. Yeah? And so we already anticipate that we could also clone from fathers, for example, maybe in the future. So we make our code robust. So let's play around with this, because this is something which is called record syntax, and I haven't showed you this yet. So these things, it's like almost the same as writing sheep, string, maybe sheep, maybe sheep. Yeah? These are the argument for the sheep constructor. But by writing in this record syntax, we are also at the same time making getters for the different parts of your algebraic data type. So in this case, we will get a function name which takes a sheep and returns a string. So let's see that in code. So the file just is it big enough? Yeah. So the file just contains like this one algebraic data type definition. Sheep. And so we can then ask what is the type of name. And as I said before, it takes a sheep and it's going to give you back a string. And so we can now create a sheep like we would normally do that. Like, for example, we could say dolly, and then nothing. That's not entirely true, but so S. And then we can ask the name of the sheep, and we get dolly. Yeah. So that's that. So in one go, we define like these getters, and we define the constructor for our sheep. And so we have maybe sheep, and we can make sheep that have both a father and a mother, and we can do all these kind of things. Okay. So let's define some operations about sheep. So the maternal grandfather. So what do we need to do? We have a sheep here, and so we have this accessor mother to get the mother of a certain sheep. And so in case it's nothing, we are going to return nothing, right? Because if it already doesn't have a mother, then we cannot access the father. And so if it's just M, then we found that that this particular sheep has a mother, and we can just use our accessor father to get to the father. And that one is going to return a maybe sheep, which is exactly what we need to return here. Okay, so if we then make the mother's paternal grandfather, it gets a bit more complex, because first we need to do the same thing. We need to check the mother, and then if it has a mother, then we have to ask the father, and then if that's nothing, we return nothing, and otherwise, if it's the grandfather, then we take the father of the grandfather, right? So I don't know about you guys, but this code doesn't look very nice, right? And the reason is that we have like this maybe type, and we always have to take into account this one annoying case when it's nothing, right? We always have to take into account that it might be that there is no result, and then we need to do something else in case it's just something. Okay. So if we do it in a certain sense in the computer science way, we could make a combinator, yeah? And so it's really essential that you follow the type of this combinator now. Yeah? So if you have a maybe A, yeah, so a maybe sheep, and you have a function that takes a sheep to a maybe B, yeah, then you return a maybe B. Is this making sense to people? So let's let's try to use this combinator. And so let's first implement it. So this combinator, the first argument is a maybe something, and so in case it's nothing, we just return nothing directly. In case it's something, yeah, we take out this something and we apply this function, which takes an A and produces a maybe B. Yeah? And so we just apply the function that we got as a second argument, and we apply it to this thing that we got. And it's really something, because it's a just X. Right? And then we return a maybe B, because this function is always going to return us a maybe B. No? Is this making sense? Okay. So now that we have our combinator, let's look how we can actually use this to make our program or our life a little bit easier. So we have a sheep, yeah, and we want to use our combinator, but we cannot use it immediately, because remember, the combinator as first argument, it expected a maybe A, right? So we wrap it in a just. Then we use our combinator, and we apply the mother on it, right? And so mother, it's going to take a sheep, and it's going to return a maybe sheep, right? And then this whole thing, it's going to be a maybe sheep, and then we use our combinator again to ask for the father, right? And so we are still doing exactly the same thing as we were doing before, right? But all the complexity of dealing with the nothing case is hidden in this combinator, which is great, right? You can just, it almost seems like that you say like, well, take the mother and from that take the father, right? And that's where we are heading. And so you can go much farther. You can then take the father, and then from that father the mother, and then again the mother, and so on. Here we take first the mother, then the father, and then the father again. And that's much cleaner because we only had to think once about how to deal with a nothing case in this combinator, and in the rest of our code, we don't have to think about it anymore because we already thought about it while we were defining the combinator. And then we are just using the same combinator the whole time, right? Everybody's following along with this? Okay. Just as an exercise, I think it might be a very good idea that you write down. Well, I see that not a lot of people have paper to write down, but at least in your head, try to reproduce the type of this combinator, because it's really essential that you understand this. So.
Could you put it on the whiteboard?
Yeah, we will put it on the whiteboard. Okay. So, let's look. Let's use the cube. So, what was the first argument?
The first argument was maybe A.
Yeah. Maybe A. Yeah.
And then the second was A to maybe A.
Yeah.
Or B, yeah, true.
Maybe B. Yeah. 2.
2 and maybe B.
Yeah. Maybe B. Okay. So this is really important. This is going to come all over and all over again. Okay. So this just thing, we could call it wrap or something, right? And so turns out that this same kind of interface, that we can use it a lot of times. Yeah? And so instead of just defining the combinator alone, yeah, what we can do is we can actually make a type class. And in this case, I called the type class chain. Yeah? And so I also have a parameter here, and it's really essential that you know which kind that parameter has. So can you pass on the cube? So as a hint, I'm giving some A here to the parameter. So the kind is star to star. Yeah. So chain itself is something that takes something of kind star to star. And so maybe that's something from star to star. Yeah. And so in this case, we can make an instance for chain by saying we are going to make an instance for maybe for chain. Okay, let's look at the two things that we need to implement for chain. We need to implement comp prime, because I already defined the combinator comp. And so it takes an MA now, an A to an MB, and it produces an MB, which is exactly the same. The only thing that we have done here is we have replaced the maybe to something more general. We have now, we don't define it just for maybe, we have defined it for everything that has kind star to star. And then we can make an instance for our chain type class. And so in the case of our combinator for nothing, it still returns nothing. And if it's just x and it gets this function f, then we call f with this x, right? And so then this wrap A, it's just A, right? Okay. And it doesn't seem that we have gained a lot at this point, but we can again write the same program, this mother's paternal grandfather. We have a sheep, and then we wrap it. I see you looking strange.
Yeah, how is it inferring that maybe is the instance of the chain type class that is going to invoke when you call wrap?
Because you use mother here. And so mother, it takes a sheep and it returns a maybe sheep.
Right, and so it infers backwards from the function you call it?
Well, there is type inference going on here, and so it looks at both parts. Yeah, it can know that it's that this one has type MB, and so all these constraints are generated, and then they are solved, and then it finds out that it's a maybe. And also in this case, because there is a type signature, right? But you can actually remove it; it will still find out correctly.
Also, it doesn't when it's doing wrap, it doesn't need to know exactly what it's doing by lazy, right? It doesn't evaluate or figure out.
Well, it needs to know that it's this particular wrap, right? Because we could have other instances. In this case, we only have one, but we could have more.
Isn't the principle of it being lazy that it doesn't really need to know which wrap it is until you use the mother later?
This has nothing to do with laziness, because this is even before we are starting to execute. This is type checking. So before you're actually running the program, there is a type checking phase going on, and in order for that to go through, it needs to know which particular wrap this is.
Is there a way to tell it, hey, I want you to use the wrap from maybe? If you're, for example, like deep in the internals of a particular thing and you don't want it to infer from the outside based on usage?
Use colon, right?
Yeah, you
Okay,
can use the.
That's maybe an upcoming
Yeah.
thing.
So for better understanding, if you change, forget about what this function returns. If you change mother to some other instance of chain, then that wrap would be that instance's implementation.
Yeah. Okay. Yeah. So I yesterday showed you Google. Or it didn't work, right? But there is like this website very similar to Google, and in case you are finding something new, or you are searching for some certain type, you can just give in the type. And so what I typed in here is exactly our chain combinator, right? No, our comp combinator, sorry. And so it's an MA, you get a function A to MB, and you get an MB back, right? And so we search for this, and turns out somebody else has already done that. And so it's exactly this weird thing, which is called bind from the monad type class. Yeah. So I kind of tricked you into understanding what the monad type class is by calling it chain, but this is it, right? There is actually nothing more to understanding the type class. So there is a lot more about understanding why you would like to use monads and so on, but this is basically it. Yeah. It's a monad, implementation-wise, it's just an interface which has this type. And so it turns out that you can use it in a lot of different places, and that's where the power of monads come in. So this is the real thing. So a monad, and so this M, which kind does it have? Where,
Star to star.
Star to star, yeah. And then return A, it wraps it into an MA, and then bind, it's an MA. It takes a function from an A to an MB, and it returns you an MB, right?
Is the thing, is that a monad then?
There is indeed a list monad, yeah. Yeah, indeed. So this is the list. There is also an either monad, there is a maybe monad, there is the IO monad, there is the function monad, and so on. And so that's that's where it actually where most people get confused. But because this is just an interface, yeah, it's just an interface, and you can implement it for lots of different examples. Yeah? For you can make a list monad, you can make an either monad, and so on. And so what we have been focusing up till now is the maybe monad, right?
Is any star to star a monad?
No, there is something which is called the monad laws, and they basically tell you how return and bind should work together. But in Haskell, there is nothing that enforces you this monads law by the type system or something. So in a certain sense, you could implement an interface for, you could make an instance for anything star to star. It's just not always going to be that useful. So to make the instance of the maybe monad, what do we do? Well, if we are binding, so this is comp, yeah? If we are getting a nothing and we get this function, well, we are just going to return nothing. If it's just x and we have this function, well, we are simply going to apply the function. And then return, that's just. Okay, and so the same thing, again, written now with a real monad. So we return s when we bind it to mother and we bind it to father and so on, right? Everybody is following? Cool.
Is it wrong to think about it of combining a set of operations that depend on each other? Is that what the idea behind it is? In general, the kind of problem space that this is solving.
So what it's solving is that you in the case of the maybe monad, what it's solving is that you don't always have to take into account this nothing case, right? You can also implement what is called the state monad, and so up till now in Tetris and in Snake, what we have done is we have made our functions that they take in the state, they do something, and they return the new state, right? And we actually implemented like a very small example where we had like this list of variables with addresses, with key value pairs basically, and every function that does something stateful should then get as an argument the state and then return the updated state, right? It turns out that that you can make a state monad, and so what you get then is that you don't have to rewrite all your functions so that they take the state as an explicit parameter and then return a new state. Yeah? You can hide all this complexity inside of in your combinator, in a bind combinator. And so the bind combinator itself is going to keep track of the state, and you're going to pass it on and pass it on until you need it, and then you need some special operators in order to retrieve the state out of the state monad itself. Yeah? And so it basically doing this threading of information of the state throughout your whole execution. In the in the list monad, that actually implements non-determinism, because you can basically apply multiple computations for all the lists inside. But let's not go there at this point. So it's a very abstract thing, and it turns out that you can implement the same interface to solve a lot of different problems, and they are not all like, it's not one category, right? And that's I think which makes it complex, because most people, they want to get like one definite answer, like this is it. Well, this is it is very abstract. This is it is this is the interface, and you can use this interface to solve a lot of different problems which don't necessarily have a lot to do with each other. Yeah. Okay, so in order to work with these monads, this is still not very nice to always put this bind in between. Yeah, you need to know that this is something that's going on underneath. But in Haskell, you have what is called do notation, and in do notation, we can write the same code that we wrote here in this way. And so this is a very explicit way. So this do, yeah. What does it do? Well, it's first going to take the father of the sheep that we provided here. Yeah. This is going to return a maybe sheep. Yeah. And so what this arrow does is it's going to take out, here we have an MA, is going to take out the A. Yeah. So at this point, F is going to be a sheep. Yeah. And then we can take, from a sheep, we can take the mother, and that's going to again return a maybe sheep. And that's going to be taken out again. So then we get a grandmother, and then what we return here at the end is the mother of the grandmother. This is going to be a maybe sheep, and that's also what we want to return. And so this is exactly the same as this piece of code. Yeah. So I probably didn't show you this syntax yet. So, but this is an anonymous function. So that's simply like, for example, does everybody know what lambdas are? I see everybody. Okay. So this is the syntax. You just have like this backslash. This is the argument f. It has one argument f, and then it's going to execute this piece, right? So we start by taking the father. That's this part, right? And then we use this bind operator, and that bind operator, remember that it's taking an MA. This is this part, and it takes a function. It takes an A and gives back a maybe B. Yeah, and so this part here, it gets like either it's this bind operator is just going to return nothing, or it's going to apply this function in case it was a just something. And so you're going to continue with this f, and then you're going to bind again, because this mother of f, it's going to return a maybe sheep. You bind it with this function that receives the grandmother, and then you return mother of GM again, which is a maybe sheep. Yeah. So certainly in this case, this code looks much cleaner or it's much easier to write than this code. And so most of the time you will not encounter this explicitly in Haskell code. Most people will use this do notation. And it also gives like a nice interface. It also shows like the sequentiality of your code, because you're passing on a function, an argument here to that function, which is then being passed on and on. Okay, I don't have time to start with this. So well, maybe just to highlight it, these are like these monad laws that I was talking about before. So if you do return A and you bind it with F, that should be the same as just applying F to A. Yeah. So why is that? Let's look at the maybe case. Yeah. Return of A for the maybe case. What is it again? Yeah, just A. And so F, it's an A to an M B, and so in this case a maybe B. And so that's exactly the same as just applying the function directly. Yeah. And then if you have M and you bind it with return, that's the same as M. Yeah. So this M, how does what should it be if in the case of maybe? Yeah, a maybe A, and then return. What does it? What is the type of return?
A to
Yeah, and so
A to maybe.
in the case of return, it's really A to maybe A. Yeah, and so this is a maybe. Let's say that it's just 5, right? And then return, it's going to take the 5 and it's going to wrap it into a just, and so that should be exactly the same. So and the last one is like you can look at it as you can change the parentheses, so the order. Yeah. Okay, I don't know if I have enough time. No, I don't have enough. I certainly don't have enough time to explain you this in detail. But it's really cool. So I'm going to still make an effort in trying to do this. So here is the whole definition of what is called the list monad, right? And so again, here we have our monad definition, and this is our implementation for list. And so return of X, it's just going to make a singleton list where this X is in, right? And so if we have a list and we have a function, and then very important, so what is the type of K here for the list monad specifically? Did you already answer or not? So, so in K, that's corresponding to this part, yeah. But we need to instantiate it for the list monad, and so it takes an A, and it's going to return a list of B's. Okay. And so what we do then is we are going to return. We are going to take all the elements out of this original list, right? And then we are going to create new elements, yeah, Y, by applying the function K, which is returning a new list, yeah, to each of these elements, right? And then we are going to take all these results into the returning list. Yeah? And so bind, it needs to return a list of B's, and so that's also what we do here. Yeah?
What's the difference between this and notation? Like, can you go to the previous slide for a second? And notation, map, mk, and m dot k, and list. Like for the list monad, the second line.
Yeah.
Is there a difference between this notation and basically mapping the function m dot?
Yeah. So yes, there is a difference. If you just map the function the function K over this list, you're going to create a list of lists, and so you still need to kind of combine all these lists together in one big list. And that's what you do with concat.
That's not kn, but k dot n. Like we had
The point-free notation.
yeah.
That doesn't make any sense, k dot m.
Okay.
I'm sorry.
Where is the flattening that's supposed to happen?
That's concat.
Because m is not a function.
No, but in the line above, in the list comprehension,
Um,
picture of the flattening here.
Well, you take out all the elements here from this list, and so you are just returning one big list of all the combinations where you return a y.
So y is not a list itself?
Y is not a list itself, no.
When you run kx, don't you get a list?
So this is all the y's for which holds that you take x's from the list m, yeah? And you take y's from the lists which are generated by applying the function k to this element x. And so,
The y a list, right?
Yeah, but I think it's the arrow. It essentially flattens. Like you're
Yeah.
saying take elements out.
you take one element out.
Like we do from m to x there.
Okay. So it's a different thing.
So, what we have in practice is a list of, like if we were to put it in numbers, right? And let's apply a function plus,
Wait a second.
right?
So let's just, well, actually we are running out of time, but let's just look at these pairs, yeah. And so here we have we take a list from 1 till n, and then we take a list of from I plus 1 till n, and we take all the pairs I and j from it, yeah. And so this is going to end up with this list. Is right, and so we can do this the same kind of thing in the list monad. And so the way that we do this is we take i's out of this list, yeah. And so this is an m of a, and we take out the individual element, and so implicitly here there is this bind operator between this part and that part. Yeah, and so here again we get I and j's, and we end up with the same thing, right? And so because we basically are going to combine all the different cases that you can do here, we can take an I out of the first list, and then we can take a j out of the other list, and we can do all the different combinations of taking out I and j's from these two lists. This is also sometimes called a non-deterministic monad, of non-determinism monad.
And the bind implementation took care of flattening the list internally.
Yeah, because you give back an m of a, m of b. You're not returning an m of b. And so if you leave out the concat here, you're going to give back an m of mb. And so this concat is to flatten. Okay, this last part, if you are not completely following, it's entirely my fault because I still wanted to show it to you, and 5 minutes is really not enough to really do this in a good way. Anyway, thank you for coming.